Hello, class 11th physics, chapter kinetic theory of gases. First, let's discuss about some of the assumptions. Okay, so first of all, gases consist of many molecules in constant random linear motion. So we know that molecules are constantly moving and their motion is random. They are moving here and there, and they are in linear motion. They are performing. Other than that, intrinsically, they can perform, each molecule can perform rotational and vibrational motion also, but we are interested here in their linear motion. Second thing, the volume of all molecules is negligible as compared to gas's total volume. So we have to assume that. Although, as you can see, if this is a container and this is a single molecule there, although it is having negligible size as compared to size of this container, still it has its own finite size, but that is negligible. We neglect its size. That's the second assumption. Next, intermolecular forces are negligible. See, if there are two molecules, okay, so if there is an atom or molecule, there is another atom or molecule, so it would have some positive part, some negative part. It is not like a scientifically expert drawing here, but I'm just drawing it in a way which make you understand that what I want to express here. So a molecule has some positive part and some negative part in it. Even in fact, if we talk about a single atom, it has some positive part, some negative part. This positive part will interact positive part of other molecule. They will do this repulsion, and this negative part, I think it is better to draw it within different color. Okay, so they will also repel each other, but here it will attract this one and it will attract that one. So there will be some interaction between molecule, but we ignore that. In order to simplify the things, we ignore that. Next, the average kinetic energy of all molecule does not change. See, individual kinetic energy of molecule differs from other, may differ, may not differ, but not necessarily they are same. But average kinetic energy we will take as average kinetic energy of entire assembly. So the average kinetic energy of all molecule does not change so long as gas's temperature is constant. So if gas temperature is constant, so average kinetic energy of all molecules is same, constant. And in other words, collision between molecules are perfectly elastic. So what are perfectly elastic collisions? The collisions in which kinetic energy remains conserved. So actually they are not losing their energy while colliding with each other. So their kinetic energy depends upon temperature only. It is not going decreasing because of their collisions. This statement is just the extension of what we have discussed here. The average kinetic energy of all molecules is proportional to absolute temperature of gas. This is what we would be deriving later on. This means that at any temperature, gas molecules in equilibrium have the same average kinetic energy. So on the basis of that kinetic theory of gases, assumptions, now the major part, explanation and expression for pressure exerted by gas, or I should say, or I must say, ideal gas. What is this ideal gas? Actually, which follows that all the requirements of kinetic theory of gases, or I can say which follows all the gas laws. So what are those gas laws? We are going to cover them later on. So right now I will say that which follow all the requirement of kinetic theory of gases. Those gases are ideal gases. Okay, so in order to do that, let's assume that there's a container, and see, it is a three-dimensional container. Although it is three-dimensional container, yet I have drawn it two-dimensionally only. Otherwise, it will create unnecessarily complications and nothing more than that. And let us suppose there is a molecule. This is a molecule. It is circular in shape, and this is I have drawn in 3D look. And it has different it is moving randomly here and there like this. It is very difficult to, oh no, it is not coming out from this container, but it is continuously moving here and there, hitting its walls. And okay, so though it is difficult to do any perfect mathematical analysis, so what we can do here, we can resolve it into three components, its velocity into three components. One is going toward x-axis. I'm drawing it with blue color with v subscript x, and other component along y-axis I'm drawing it with green color vy, and third one is coming out. And as I have drawn a two-dimensional figure here, so third dimension I am drawing as a dot only. You can see a dot here. This dot is showing that that velocity is coming outward, and I am marking it as vz. And remember that from vector calculus we know that this v squared, that is square of this velocity, its velocity is equal to square of velocity of its components. This is much better to write. For single particle, this is for single particle. Although for large number of particles we have to take average of these squares. We don't use the term average, we call mean. So it will look like, oh, I can use a trick here. For large number of particles we have to take average. We call it mean, and to show that we have taken mean we use this angular bracket. Few people put a bar over a quantity, but that creates confusion. This angular bracket is specifically used for to show that we have taken mean for large number of particles. Number. So, if we want to find pressure exerted by this gas, we have to move from one with single particle. For single particle, initial momentum along x-axis, is m vx. All right. Now, as its collision with wall is perfectly elastic, so with whatever be its speed here, it will remain same. Only direction will change, so that you can find it out of yourself that how by this momentum remain conserved. So final momentum after collision. I'm not writing all these things actually. So final momentum will be minus mvx. mvx. Now, what is change in momentum along x-axis? So final minus initial, that will be minus 2, oh god, mvx. So force exerted by the force exerted on, because its momentum has been changed, so force exerted on the molecule by the wall, force by the wall by the wall on molecule. On the molecule, I'm writing on the molecule, on molecule, mo only. So that is by Newton's law, change in momentum upon time. So there is delta t time in which this entire whatever we have measured has taken delta t time. So in those delta t in that delta t time, all of those molecules which hit the wall will produce a force, and due to that force there will be some pressure, but that is wall on the molecule. This has been exerted by the wall on the molecule, but we have to find force exerted by the molecule on the wall. So all right, we can write it, and later on we can find how much pressure, how much force molecule has exerted on the wall. So we know that oh, it looks like plus, it is T actually. Okay, so force exerted by the molecule is that will be negative of this, so it will finally become positive. See, actually this positive negative circus is not that much important, because we are taking this positive negative as reference to our convenience. So if I took I would take these this negative, then this would be positive, then this would be positive, and then it will be negative. So but we have to think about not about these positive negative, but what is the actual theme, what is the actual reason behind this. Okay, so here it is. Now let us suppose there are small n number of molecules per unit volume. Number of molecules per unit volume. I'm not writing it, I have just stated it. So I have just asserted it. So you can note down that this is small n, number of molecule per unit volume. It is also called number density sometimes. So but we are not going to use this right now. What we are going to use also, because it is number density, so it will be same for any sample, any small or large sample of this gas, n dash, n prime to be very precise, upon v prime. So what is this n prime? And again I'm asserting only, so you take a note of it, that this molecule is covering a finite volume. V dash is the volume of that covered volume, and n dash is the number of particles in that volume. And now the question is, what is V dash then? So V dash, in fact V prime actually, I have a habit to call it V dash, but it is V prime. It is area of that molecule multiplied by distance covered by it in delta t time. This is delta x. It has traveled delta x distance. So how much volume it has covered? Its area is A. Its total area is A. Surface area we can say. And so this volume it is covering. So n dash, that is number of molecule found in this region, will be equal to small n, number density, times V dash. V dash is A delta x. But this number of molecules, we are not sure about that all of these molecules are going to hit the wall. For the sake of symmetry, we will say that half of the molecules are going this way and half of them are going opposite way. For the sake of symmetry, we can make those assumptions, we can take those approximations. So all right, so number of molecules, MO, molecules actually hitting the wall in time delta t is this much. So force exerted by force exerted in this volume, which volume? This V prime volume. In this volume it is along x-axis, so I'm writing this is equal to these number of heating molecules and multiplied by this force which is exerted by single molecule 2 m Vx upon delta T. Oh, it is looking like multiplication sign. So I have to change it so that it would look like no. So it is Na delta x. Okay, this delta x by delta T. And one more thing. I should cover up this because I'm taking it for large number of molecules. So instead of writing this Vx, I should replace this with that average value. Okay, so in the next step I would do that, but because here we have this delta x by delta T also, which is also equal to Vx. So it is now, oh, it doesn't matter, but it would look, okay, 2 will get cancelled. There will be n only now, n a m and Vx square. And in this step, I would replace this Vx square with average value. That is mean. We can't take simply V square. It is actually mean value for all the particles. And now, we will divide both sides by a, so this will get cancelled. This will come on this side. We can say it like this also. So here it is fx upon a, which is equal to n, number of molecule per unit volume, times m, mass of one molecule, times Vx square. And this is actually pressure. And we are not bound to write it like pressure due to pressure along x-axis. We don't require to write it like this because pressure is a scalar quantity. So it is independent of that x-axis, y-axis, z-axis. Pressure is just a pressure. But this V of x is just spoiling everything. It is indicating that it is direction dependent. So we have to make it direction independent. Now, for random motion, you should write it here. For random motion, the average values, actually this Vx square and then mean is equal to Vy square is equal to Vz square. Let me explain you why is it so. So let us suppose in a container there is a gas molecule. Its velocity has a greater x component and lesser y component and least z component, and there is another molecule which has greater y component, lesser x component and mediocre z component. There can be some molecules which has entirely that x component, no y, no z, but these molecules are randomly moving here and there, and not specifically. It is not like a wind is blowing in particular direction and then we can say that no, this criteria is not valid. No, actually we are having these enclosed in some chamber, and so they are not moving in some preferred direction. They are randomly moving. So in a close approximation, it is better to conclude that square mean of each of their component will be more or less nearly same. So we have considered them equal to each other. Okay, using this expression and initially what due to that vector concept, what we had the information, we can conclude that this square mean value is equal to Vx square plus Vx square plus Vx square, because all of them are equal. So in the place of these two, I can write Vx. So it will be 3 times that of Vx square mean. It means that in the place of this Vx square, we can write 1 by 3 this V square mean. So the expression changes to 1 by 3 n m v square average. No, it is not looking great shape. Oh, that's also not good. Yeah, this is looking much better. So this is the final product. Yet there is a technical term I have to introduce here. See, for these random motion, instead of velocity, we have another term which is called RMS velocity. That is VRMS. We'll talk about it later on, not in this video, but in some other video. So VRMS is actually, it goes in reverse order. First, take the squares of all the velocities, then take mean of each of them, and then take root. Here it is. This is VRMS. So if I square both the sides, so it will be VRMS square is equal to this oh god, this square mean. So the conclusion is that in this final formula we can write, instead of this, we can write VRMS square. So this P equal to 1 by 3 nm. This n is actually number of particle per unit volume, and now I can put it value of this n equal to the value that earlier we introduced, that is here for whole assembly, this one. Actually this one, here it is, for whole assembly, not for this small part now anymore, for whole assembly, that is capital N by V, where V is the entire volume of this container. So it is N by V. Remember, few publishers write capital N as Avogadro number. If I have to write Avogadro number anytime, I would write N and subscript A. If there is only simply N, then it is simply number, any number. So make sure whenever you see the expression related to this, then if you see this N, try to find its specification. What is this N? They will not directly write N. They will specify that it is either Avogadro number or simply number. Now, these are number of molecule, and this is the mass of one molecule. So it means N multiplied by M will give total mass of the gas. 1 by 3 total mass of the gas. Purposely I am writing it W, weight of gas. I know I'm using wrong term. Weight is something else, something different, but I can't do anything. Small m I have taken as mass of molecule. Capital M is actually molar mass. So that is why I have to write this as W, or if you have a better symbol for that, write down in the comments. And this is VRMS square. And this is, actually it is mass of gas. Read it as mass of gas upon volume, which is density. So final answer is P equal to 1 by 3 rho and VRMS square. So this is the final undisputed formula, and with the help of this, now we will derive gas laws and some new concepts, how kinetic energy is related to temperature and all those things. So I'm ending today's video here only. That's all. Bye bye.